Hey everyone, and welcome to my talk, Intro to Hardware Hacking with a DRM'd LED Therapy Mask. My name is Jamie. My background is in electrical engineering, specifically embedded systems. I kind of accidentally became a software engineer for a little bit, and now I work as a security researcher on Grimm's sci-fi team, taking apart cars and hacking other cool things. So this story begins quite a while ago in the pre-COVID before time. I was actually at a bar and a friend texted me about this really, I didn't know at the time, but really creepy LED face mask that she bought that stopped working pretty soon after she bought it, and she needed some help. So I'm like, yeah, that sounds fun, sign me up. I was actually still at the bar doing research on my phone and reading about it. The idea is that the inside of the mask has red and blue LEDs that light up, and the idea is that it, treats your skin. I don't really know if it works, but that's not the point of this talk. So of course there's this part, and then there's a little activator kind of remote that it plugs into. This has two parts to it. One, it powers the mask because of the batteries in the back. And then the second part is that it shows you how many uses you have left. It starts a timer and then it shows you how many uses you have left. And I don't mean how many uses you have left before the batteries run out. I mean how many uses you have left before the activator bricks itself and you have to go and buy a new one for $15, throw away the old one. Otherwise, your little mask thing doesn't work anymore. And you're supposed to use one 10-minute session a day. You get 30 uses, which means that you're going to have to throw one of these out and buy a new one every month, which I think is kind of bullshit, right? You've already got this kind of creepy Friday the 13th mask, and you've got planned obsolescence built into it. Such that you're throwing away perfectly good electronics just to make a little bit more money. So needless to say, I pretty quickly started disliking this mask before I ever even saw it in person, and I got drawn into the idea of figuring out what was going on with it. So it turns out there are plenty of guides online that tell you how to bypass the check in software by just a quick hardware fix where you take two of the pins and you short them together, and it completely bypasses the whole software part of the device. And that would have fixed the problem in like 5 minutes, but I didn't want to take that approach. I wanted to do something a little bit more complicated and time consuming. I gotta stay on brand. So I wanted to take a different approach. I wanted to see what was happening in software, and if I couldn't change, what was going on there. The product has since been recalled due to eye damage reasons. So by the time I finished this side project, my friend didn't want to use it anymore, which is fine. It wasn't a very practical project, but I still learned a lot, and it was pretty fun. It's a pretty simple design, but it works as a neat little example for hardware hacking in general, which is why I'm sharing it in a talk today. So, step number 1, you need to find something to hack. This probably won't come as a difficult step to most people, but I want to cover it anyway. I already told you what I chose for this step. My motivation was helping my friend out, learning a little bit. I wasn't really trying to save money, and I imagine that most of you aren't, motivated to save $15 a month to go through all this work. There are other motivations happening. For example, you might be looking for some kind of vulnerability that gives you unintended access or control. And because that usually means code execution, we think of that as an exercise in software engineering or software reverse engineering. But in order to get to that point, you need to do some hardware hacking first. In this talk, I only had one copy of the device, which you'll see kind of turned out to be a little bit of a hindrance. If you're doing this for work or security research, hopefully you have access to multiple copies so that if you break one on accident, it isn't a big deal, or you might need to break one on purpose. For example, you might want to pull off a memory chip and then dump the contents. So if you don't get one of these, or you don't get enough from your customer or whatever, there are other ways of buying parts. You can, just buy them off the shelf like a normal person if you're trying to do something that's IoT or, consumer products. If you're looking for more specialized equipment, you can check out eBay. This photo here is a search for trucking ECUs, but I've seen a lot of other stuff on eBay that seems like it really shouldn't be for sale. So step 2 is to take it apart. Once you have the thing you want to hack, you need to get full physical access to the board inside on both sides. In this case, I only needed to take out a couple of screws, and I just used a screwdriver. If it's a complicated process, I recommend that you take photos, or if there are outside connectors that kind of attach in a difficult to remember way, just take photos, help yourself out later. And then also hold on to the casing because you might want to use it later. For example, I partially reassembled mine because the battery holder was very useful. But you might not be so lucky. For example, if you do a lot of work with ruggedized automotive equipment, you're going to have to go through more work. For example, in this video, which is from searching remove epoxy on YouTube, it shows how for certain types of epoxy you can heat it up, such as in boiling water, and then either peel or chip away the epoxy. In another example, last year one of my coworkers helped me sawzall a ruggedized case apart, which unfortunately I can't share photos of in this talk. So once you have the board free and you can see both sides, step 3 is to identify components, which is a 2-part process. But before we get into the details of that, we need to talk about reference designators first. So when PCBs are designed and manufactured, the engineers put markings on the silkscreen layer to help identify parts for troubleshooting, design review, things like that. For each reference designator, there is a letter and a number. Each letter is going to correspond to a certain type of part, and these are standardized across almost all boards. So C is for capacitor, so anything with C and then a number, you can assume it's a capacitor. So for example, in this first picture, we have C8. Resistors use R, jumpers or connectors use J, and then integrated circuits use U. So of all the types of components, the U components are going to be the most interesting to us because that's where the software, the logic, and the control is implemented. So here's the whole board with the parts identified. The top side only, there's nothing really going on the back side of this board. In general, we want to focus on the components that involve logic or communication, and that is highly correlated with the U reference designator. So the first half of step 3 is to get photos. Obviously, I already have them because I just showed them to you, but now we want to zoom in on the parts that are most interesting, like the microcontroller, memory chips, communication-related chips, all of the U reference designators that we just talked about. But if you get photos of other things too, that's totally fine. So reference designators tell us which type of part. We already found those on our boards just by holding it in our hands and looking at it. But now we want close-up photos. These photos need to have high enough resolution to see the markings on the electronic components. In this Arduino example here, you can see like the really faint tan text on the components. That is what we're after. So you don't need to say enhance when you zoom in on these, but I think it helps. I circled the U components on our board in this photo, and we're going to take really close-up photos of each of those. If you have jumpers or connectors or other interesting parts, get photos of those too. If you have a lot of parts on your board, which isn't really the case here, we only have like a dozen, then consider making a spreadsheet to keep track of things. So now that you have the pictures, you said enhanced when you zoomed in, you've got a clear view of the markings, which in this photo are only a few millimeters in width. It's actually this part right here, which you can see is tiny. So it says ATML, H440, 466D, etc., kind of like an eye exam. So now that you have those, step 3B is going to be just Googling things, which I know, pretty sophisticated. And this is a little bit more of an art than a science, which we'll get to in the next slide. On this, the Atmel is a brand. You might have a logo instead. You have the part number, and then you have some kind of variation information, or maybe batch information for that part. So when you go and Google this, you don't want to just put the numbers in by themselves. You want to put something in like SMD for surface mount device, or datasheet after it, and then play around with how much of it you include. You might not need to include the brand. You might not need to include the batch name. Just play around. Like I said, it's not really science. So in this case, it turns out that the part number looks like it corresponds to an Atmel EEPROM chip, which I think makes sense here, which is external memory for the microcontroller. There's also a website called smdmark.com. You don't always get hits on here, but I find it is still worth looking. In this example, I Googled 7533, which is actually this even smaller part here. And I got some results back that suggest that it is a LDO, which is a voltage regulator. All right, so the important thing to keep in mind here is that there are a lot of very similar parts, and you're going to waste a lot of time and effort if you go into the next steps using the wrong datasheet. So you want to do some kind of due diligence to make sure that you have the right one. And that doesn't mean that you need to read the whole thing top to bottom. You might look for information in the datasheet about what markings it says will be on the parts to kind of cross-reference that. But what I like to do is measure the power and ground pins to see if they match up with the datasheet. So for example, if the datasheet says that pin 4 is going to be ground, and then pin 8 is going to be power, or 3.3 volts, measure that and be sure. If they don't match up, you don't have the right datasheet and you need to keep looking. If they do match, that doesn't necessarily mean that you did it right, but if they don't match, you probably did it wrong. So in this case, I thought I had the right one. I measured it. I traced the pins to power and ground. They didn't match up, so I kept looking. I ended up finding it. It's kind of a uncommon and now end-of-life part, but I did end up finding a datasheet that matched. So as best as I can tell, these are the components that our board has. So a Atmel EEPROM, Holtec LDO, voltage regulator, Seacoast MOSFET, and then I don't know what kind of microcontroller it has, because it is covered with epoxy, and in this case, it is only covered with epoxy. So if I were to try and remove this, there wouldn't be any plastic packaging underneath. It would just be the bare silicon, and I don't really want to risk destroying it or damaging it. And normally the microcontroller is one of the most important things to identify, and on almost any other project I would find a way to identify it, but I thought maybe in this case I didn't need to. For the other components, the LDO tells us that the EEPROM and the microcontroller are powered off of 3.3 volts. The MOSFET is part of that circuitry too. I have a way of powering the board through the batteries, so that information isn't super useful, but it's good that I know it, and if I had to, for some reason, power the board off of, power part of the board off of something besides the original power source, then that would be pretty useful. Step 4 is more datasheet reading. Lucky you. You still need your multimeter. You probably want some coffee. You have the data sheets that you had before, and now we're going to read them in more depth. You already, did a cursory check to see if they fit. Now we're going to really dig in. So earlier we looked at all the components on the board. We narrowed it down to the U reference designator ones. We found the part numbers for each of those. Well, not quite, not in my case, but we tried to find the part numbers for each of those. We read some data sheets, and then we narrowed it down further to the most important one. So for example, we decided the LDO, not that useful to us. So for the remaining things on our list, we're going to read as much about them as possible. For each one, we're going to think about what the purpose of the component is. Can you summarize what it does within the context of the board? How does it communicate? What parts is it communicating to? What data do you think it might be sending? Does it have any security features? Are there measurable pins that determine some kind of hardware configuration like a write protect pin? Is there anything else important about the chip or unique about the chip that you should make note of? For example, the double EEPROM in our case, as shown in this photo here, it has its own instruction set that we need to understand in order to talk to it. So at this point, you want to look at the pinouts and manually or mentally or physically with a DMM trace the connections. This might be difficult due to how the board is made. If you have an expensive board, it might have internal layers, it might have ball grid array parts that make it kind of hard to trace, and you might have to get creative. We don't have this problem because this is a pretty inexpensive board. So because it's so simple, we could probably reconstruct the whole circuit diagram in this for this part or for this board. But that usually isn't feasible, and it's often not necessary either. So we want to focus on how the board is powered and kind of represent that. Communication between the components and then into and out of the board, where memory might be, where logic is implemented in microcontrollers and things like that. And then specialized areas like maybe you have a CAN transceiver, which has some overlap with the communication part. So put all of that into a block diagram to help yourself out, or if you're working with other people. For most of this, you don't need to understand it to a double E level. Back to our power example, you don't really need to know the electrical details of the power regulation circuitry, just that you have batteries that are between 5 and 6 volts, and you want to regulate that down to a lower voltage because that's what the other parts run on. We want to focus on communication protocols and where the software and logic is. So for this board, the way that you talk to the double EEPROM is through a 3-wire SPI protocol. And the double EEPROM is there for a reason. Since there isn't a whole lot else going on this board, I think we can probably safely assume that the microcontroller is storing the count of remaining uses for the mask in the memory in the double EEPROM. So from the datasheet, I identified which specific pins on the double EEPROM correspond to the 3-wire SPI communication. I added those to my diagram. Obviously, this example is pretty simple, but having the blocks, maybe the part numbers, and then the pins are going to make things easier on your future self, unless you're able to do side projects in one sitting, which in that case, hats off to you. I definitely took a while getting this one done. So now we're finally getting to the fun part, or the more fun part. We're going to need a few more tools for this step. Part of the reason why we spent so much time talking about communication protocols is because it's going to help determine our strategy and then also the tools that we need. So now that we kind of have a good idea of what is happening on this board, we want to think about how we might gain access via methods of communication that we found on the datasheet. In our case, it's pretty much just that 3-wire SPI. In other cases, you might have a whole list of ideas. So make a list, prioritize it by likelihood, by the tools that you have, by what the likely benefit or end result might be, and then work down your list. But we don't have that here. We narrowed it down to two components. One of them is covered in epoxy. My overall goal is to re-enable the functionality of the mask by either altering the device logic in the microcontroller or increasing the stored number of uses left count. So we can't get to the microcontroller right now, but we have pretty easy access to the EEPROM. We know how it works. We think that it is storing what we want to alter, so let's go with that. So if this were a different board, there would probably be more options. There might be a serial line, there might be JTAG or other debugging things. And the reason that those methods exist on boards is because engineers usually don't get things right on the first time, and they build in methods so that they can get access and debug things. And hopefully for them, they have turned it off in production in a way that isn't easily reversible. If they forgot to do that, then lucky you. If they have done that, then you need to find some kind of secondary flaw or some kind of flaw in the security of that access method to get closer to your goal. So back to our board, we want to talk to the EEPROM with 3-wire SPI. We need to find a tool that does that. The Bus Pirate, which costs about $20, does that. So, and I have one on hand, so we're going to use that. There are other tools depending on what you're trying to do. For example, a JTAGulator is going to look for some on-chip debug interfaces and interact with them. I have a link at the end that helps you kind of narrow down what you're looking for. So the end goal on most of the devices, not this one, but most devices will be code execution. So like I said, come up with a list of options and then prioritize them and then work your way down the list. So for this one, we are going to try and change the count to a higher number, and then if we can do that, kind of build on our success and see if we can't remove the software check altogether. So I know the chip, I know the pins, I soldered leads on, which is before I got smart and ordered a chip clip, which makes your life much easier. Anyway, I don't want to go into specific settings here. I have a blog post for that. But I wanted to just read everything first. So I read the datasheet, figured out how to send a read request. I found that everything in memory was FF except for 4 bytes. 2 of them were either 0 or close to 0, so I thought that's probably my count. The other 2 I wasn't sure about. I read the datasheet some more. I learned how to send a write enable, a write message, and then a write disable. So here I'm reading location hex 50, which was one of the count variables. There were actually 2 count variables. And then the second part there, I am writing to the 2 count locations, book ended by the write enable and then write disable. So if your first attempt doesn't work, keep moving down the list. This actually worked pretty quickly once I figured out the protocol. Here is a photo of having 98 uses left, so mission accomplished. And I was feeling pretty good about my progress. I made some changes, and then I ended up in this weird error state where it just had 2 dashes on the display and it wouldn't turn the mask on. I tried programming again with something that worked before and it still didn't work. I read through a bunch of Neutrogena documentation, which was thrilling, to try to figure out how to reset the device. I pulled the batteries out, I disconnected the Bus Pirate, I waited, I plugged it back in, it still didn't work. And what it ended up being the issue was that there's a capacitor that was charged up and I just wasn't waiting long enough for it to discharge, so the system was never actually fully powered down. And I was still working off the previous error state. I realized this by measuring the EEPROM's power pin. So I shorted it out to, fully power it down, and then I was back on track. So the point of the story isn't just to, share my moment of panic, but to point out a couple ideas that will probably help you later. So the previous sections talked a lot about understanding things at the individual component level, but you also need to understand how the product works as a whole. And there might be documentation kind of aimed at consumers that will help you. Once you have something working, you want to stop and write down exactly what you took. If applicable, you want to have a known good state that you can back up, that you can, revert to. And then for electrical things, you need to prove it out with a DMM. If you have capacitors on the board, then powering it down isn't going to be instantaneous. And even if you know this, you might forget, or you might just be really impatient like I am. And hardware really only cares about the physical reality of things, so you need to measure it and be sure. So at this point, we're able to alter the EEPROM and restore our activator to a working state. But if I have 98 uses left, that only gives me 3 months. And because of the byte and the display, I'm kind of capped at 98, 90, 99, 98. So I'm trying to figure out how I can permanently bypass this check so I don't have to, get out my bus pirate again in 3 months and update it. So this is what I mean by persistence. If this were another device, I might try to get to a step where I don't have to go through a really error-prone or tedious setup process like glitching. I want to do something that would make future access for myself easier. So I might re-enable a currently disabled communication method like a serial line or something. I might add my own user. I might use access for one component to get into a different component. So for this case, I didn't have quite as many options. I didn't actually get persistence in the way that I wanted, but I did try quite a few things. I looked for a write protect pin, but this one doesn't have it. I tried to cause logic errors with the 2 count values to see if maybe they didn't check for some things, but that's actually how I got into a bunch of error states. I can't do the software write protect because each message from the microcontroller is bookended by the write enable and write disable messages. I tried shorting out different pins one at a time to see if I could create some kind of unusual failure state. And I also tried changing the other 2 EEPROM values. So what else I could have tried was to remove the epoxy on the microcontroller, identify it, see if I could reprogram it, see if I could dump out some of the information. Or, at this point, I've put enough work into it that maybe I should just use a hardware jumper, because that will have solved, my goal of persistence. So, of course, this section would have been way cooler if I actually, got persistence. But I think I reached my educational goal. My friend didn't really want to use it anymore. I'm going to chalk it up to a win. And if I'm going to start replacing hardware components, I might as well just put a switch in and reverse engineer some of my other side projects that have been lying in wait. So altogether, those steps are: find something to hack, see if you can't get multiple copies of it, take it apart so you can get access to it, identify what is on the board using reference designators, close-up photos, and then Googling. Read the data sheets and come up with some ideas of how you might get access. Make a list and just work your way down. Try to avoid the pit of despair by taking good notes and doing what you can to help your future self out. And then see if you can't establish persistence or gain access to something else on the board. And if you walk away with nothing else from this talk, remember to take a lot of good notes and get your data sheets right to help save time later. So here are a couple other resources. We have the Hardware Hacking Village at DEF CON. This GitHub link, which has a ton of great resources. There is a book called Hardware Hacker by Bunny. Grand Idea Studio has a bunch of cool guides. If you work on your own electronic projects, that will help as well, because if you can understand how something is built, it is way easier to break it. And then maybe you can try out some of these ideas with some hardware that you have lying around your house. So that is all. I hope you enjoyed this talk, and thank you everyone so much for watching.